All right, I guess we're ready to get started. So, welcome everyone. Thanks for joining the working group on active B stars. Uh, Bi-monthly now, I guess, series of online seminars. So it's my pleasure to be kicking off the 25-26 season. And today we're lucky to have Dr. Abigail Frost with us. So Dr. Frost completed a master's degree at the University of Exeter before then completing her PhD at University of Leeds. Then did a postdoc at KU Leuven and is currently a staff astronomer at ESO. And Dr. Frost will be talking about the multiplicity of B stars and its effects. So without further ado, please take it away, Dr. Frost.
Great. Thanks very much for having me. It's a pleasure to be here to be able to speak to you all. And yeah, today I'm going to talk a little bit about the work that I've been doing recently, looking at multiplicity stars with VLTI, and just basically showing the effects that it has on B stars and their light. So I don't have to go too much into this background because, I'm sure all of us care a lot about B stars and we know why they're important. But, just for the sake of it, in case there's any newbies or students around, I just will go through a bit of background. So B stars, I feel like I study massive stars generally, both O stars and B stars, and I feel like even though O stars get a lot of attention because they are the most massive and they're the progenitors of black holes, B stars are still very important and create their own unique sets of phenomena and affect a lot of important processes within the universe. They're of course the originators of neutron stars and associated pulsars, which have been very important astronomical clocks, and given thanks to their periodic variations for many decades now. And in terms of the influence of massive stars, a lot of the very violent feedback that we get coming from massive stars in terms of supernovae is going to come from B-type stars. When you get to, here's just a couple of plots from a review by Hager, Miller, and Mandel in 2023. On the left, you can see kind of the fates we expect for stars at solar metallicity on the left and also at zero metallicity on the right. And you can see the mass at the bottom here. And so a lot of the supernovae that we expect essentially will be coming from kind of the B star rather than the O stars. We expect once most stars get to a higher mass that they can just directly collapse into black holes. But so a lot of the supernovae that we see in the universe, especially these type 2 supernovae, are going to be coming from B stars. And so if we want to understand these very, very important feedback events, we need to have a good understanding of B stars and their processes as well. B stars also create gravitational waves, so a very hot topic at the moment, particularly these long-inspiralling mergers and long spiraling gravitational wave signals that come from neutron star mergers. So there's a picture on the left from this kind of first, one of the first of these kind of long spiraling events that was detected with LIGO. You can see the when you see the O-star kind of blip, it's very, very quick. But here we're able to see the entire inspiraling process. And that is, again, something that's more unique to neutron star mergers than it is to black hole mergers. And also the gravitational waves with electromagnetic counterparts often come from these kind of neutron star mergers as well. And you can see an example of one of the first EM counterparts that was in-depth studied here, looking at the optical spectra 1.5 days after merger and how it evolves through these different colored lines here. And so again, if we want to understand these specific types of mergers, then we need to understand B stars as well. And B stars are also important nucleosynthesis engines in our universe as well. Of course, they are very important for the rapid neutron capture process, and everything you see here in this nice periodic table, which is in orange, is related to, again, synthesis from emerging neutron stars in this process. So a lot of what we find here on Earth, or a lot of the more complex things that we find here on Earth, are related to the activity and behavior of these of B stars. And I guess my main takeaway from this is that, and a lot of what I've just talked about is actually dictated by the multiplicity of B stars. We won't get these mergers without having at least a B star binary system at some point. And this plot here from Gaia 2023, it's not super legible, I'm afraid, but basically I'm just showing it to illustrate that there's a huge amount of complexity that can arise from the multiplicity of these stars, depending on whether they have massive donors, for example, in blue, this blue shaded region, or if they have less massive donors in yellow. There's still huge map of possibilities that binary systems even can go through just by having that one extra companion at a close separation. And so if we want to understand the influence of B stars, the evolution, we need to understand this multiplicity as well. And just to, again, emphasize this point and to show a couple of these pathways in a bit more detail, here you can see two kind of binary evolution pathways from a review by Torres and Van Heuvel. And on the right, on the left, we have a black hole and neutron star merger, and on the right, we have a double neutron star merger. And basically, the takeaway here is that we're not just having one interaction within this binary system, we're actually having two to get to these compact object mergers. So, it's not just one star goes through mass transfer and then it's done. It really is a continuing and complex process, and we have to probe these kinds of pathways at multiple different points throughout their lives if we want to understand the processes involved and how we get to these compact object mergers. So when it comes to probing stellar multiplicity, we kind of need to use different observing techniques. This is a plot from kind of an IU proceeding by Uksana in 2017. Essentially, for a typical kind of massive star distance of kind of 2 kiloparsecs, we're looking at the different techniques that we would need to probe different separations of just a binary system. So we can see that for the closest separations, kind of between 0.1 and 1 milliarc second, or in this case, for this 2 kiloparsec distance, 0.1 to 1 AU, then photometry and spectroscopy are great techniques to use. But this isn't the entire separation range that could probe, and so we also need to consider other techniques, for instance, interferometry, imaging, coronagraphy, and all of these probe different separation ranges of potential companions. And the separation ranges relate to different kinds of interactions or evolution that we can expect for the binary system throughout its life. Obviously, the very close binaries we know are most likely to interact and are likely to, and are the only ones that are going to kind of go through mergers and things. But also it's related to the formation mechanisms of these binaries as well. So if we want to understand the formation and evolution of binaries, we need to probe this whole separation range, really. And that's why using multiple techniques is very powerful. And particularly in my work, historically, for kind of the past 5-6 years or so, I've been using a lot of data from VLTI or interferometers, sorry. For example, the very large telescope interferometer here in Chile, which I now work with as part of my job as a staff astronomer as well. So, I mean, the main reason we use interferometry as a technique is just illustrated here. We have a limit that we can build our telescopes to, and that limit affects kind of the resolving power that we can have. So, if you want a better spatial resolution, you build a bigger telescope, and the biggest telescope at the moment is being built down here in Chile with the ELT. But even that is like a difficult limit to reach, mostly financially, but also technically. And so if we want to reach even larger kind of resolving powers, we have to combine telescopes at great distances to reach kind of these very, very high spatial resolving powers. And so in this case, the resolution is dictated by the baseline between those telescopes, or the distance between the telescopes, rather than the individual mirror size of an individual telescope. And because we are combining light from different telescopes, we move away from this kind of PSF view and move towards fringes, like you can see in this pattern here. And that is where we derive our observables, and that's how we can get our information from the system. And so for the VLTI, which I'm going to talk about a bit later, we're kind of pushing to milliarc second scales. I think around 3 milliarc seconds is kind of the limit that we are able to push to with this interferometer. Oops. And because we are combining the beams from telescopes, we are not getting a complete view of the source as we with imaging. We're dealing with Fourier space rather than imaging space because we are interfering the light from the different telescopes. And so whenever we observe with an interferometric array, we are probing parts of this Fourier space, or this UV space. And so instead of thinking about coordinates of X and Y, we're thinking about U and V, as you can see down here. And the specific points of the source that we are probing will directly relate to the arrangement of the telescopes that we have on the ground. And each pair of telescopes is giving us a probe of a different point in that UV space. And so by combining, in the simplest case, like you can see here, we just have 2 telescopes, but in most cases we have more than 2, so that we can get a better fill of this UV space. And also a good way to increase your sampling of this UV space as well is to observe multiple epochs or to observe over time. So as the sky moves, you're also covering more of that UV space as well. And so what kind of info observables are we getting from these fringe patterns? Well, 2 key ones that we usually get from our interferometers are the visibility and the closure phase. And the visibility tells us about the extent of the source. Essentially, this is related to the amplitude of the combined light that we get from the interferometer. And different visibility profiles can already give you a very quick idea about the spatial extent of your source. For example, if you have a clear trend off with spatial frequency, then it usually implies that you have a kind of extended structure. So in visibility terms, if you have a visibility of 1, that means you have an unresolved source. Your interferometer doesn't have the spatial resolution to resolve the edge of this source. So basically you're looking at maybe an unresolved star or something like this. But if you begin to see that visibility drop down towards 0, that means you're resolving your source. So maybe you're looking at an extended disk. Maybe you're looking at a very, very big star and able to resolve its radius. And that's what we're dealing with here. And also, if we're looking at binaries, a telltale signal that you're looking at a binary is that you see some kind of sinusoidal shape in your visibilities as well. Another key observable we have is the closure phase. This is retrieved when we have at least 3 telescopes in an interferometer. And because in the optical, the atmosphere is varying so quickly, we don't retrieve direct phase information at each of the telescopes like we do in radio interferometry. And closure phase is essentially us using the spatial offset of the different telescopes to retrieve an overall phase parameter from the source that we're observing. And this closure phase can tell us about the symmetry of our source. If you have closure phases which are equal to 0, then you have a very symmetric source. But if you see a clear deviation, then that tells you have something asymmetric that you're looking at. And in order to retrieve any of these parameters, we have to observe kind of a well-characterized calibrator star, so maybe a point source that we know should have, with perfect conditions, visibility equal to 1, for example. And so we use that as a reference point for calibrating all of these, calibrating our science sources, essentially. So a recent work that I've done that I'll talk about a little bit now has been about characterizing the cell multiplicity in the kind of 100 millisecond range using interferometry. The interferometer that I work with generally is the Very Large Telescope interferometer. This is at Cerro Paranal here in Chile, up in the desert near the city of Antofagasta. And it's a full telescope interferometer. You can either combine the light of the 4 small auxiliary telescopes that you see down here. Excuse me. Sorry about that. Yes, sorry. So it can combine the light from these 4 auxiliary telescopes. These have a diameter of 1.8 meters. All these 4 much bigger unit telescopes, or UTs, which have a much bigger diameter of 8.2 meters. The benefit, though, in most of our interferometry data at the VLTI is actually taken with the ATESO, and this is because we can move them around. You see these rails here, and so we can change the baseline configuration. We go through 4 different configurations every month, from small, medium, large, and extended, and the maximum baseline length for the extended configuration is around 220 meters. We also observe with the UTs, these can't move obviously, but they give us a better sensitivity, and the maximum baseline for these guys is 130 meters approximately. And so because of this flexibility of the baselines, we're able to reach some nice millisecond scales. And there are 3 instruments that exist on the VLTI. We have Pioneer, which is what I will be talking about in a second. This is the H-band interferometer. It's a limiting magnitude of around 9 magnitude with the ATs, for example. You have typical total observing times, so that's including your science source, but also your calibrator of around 30 to 45 minutes, depending on how faint your source is. And there's also 2 other instruments. There's Gravity, which I'll talk about a little bit later, and also Matisse, which is more mid-infrared, so operating in the L and M and N band. So here's an example of some of the data that you can get from Pioneer. So I already mentioned before that we're probing UV space, and that's what's shown on the left here. Basically, each of these color points corresponds to a different pair of telescopes in the array. So that's what that pair of telescopes is probing on the sky. And that's the point that they are contributing to our coverage of UV space. In the middle here, we have our closure phases that I mentioned, and on the right, we have the visibilities. And so at the top here, we have the points with error bars are the data points, and then the model that I've been fitting to these data is in the line here, and we just have the residuals on the bottom. So yeah, in order to interpret the signal that we have, a very common way that we do this is through geometric modeling. So we model the intensity distribution of, for example, a uniform disk or a point source or a combination of these. And by doing that, we can try and work out the geometry and the characteristics of the system that we're looking at. And so here, you can see a model image that is fitting this data. It's a 2-point source system, so a binary system. And this is giving us a good fit to the visibilities and also to the closure phases. And basically the variation here is caused by the fact that these two are not perfectly equal, which is why we're not seeing this perfect kind of sinusoid. But the secondary is kind of around 10%, I think, the brightness of the primary, and that's causing the asymmetry in the system, so there's variation in the closure phases. But we can still see evidence of that sinusoidal pattern that we are sampling with our UV coverage because it is a binary system. Usually we determine the errors for this in bootstrapping. So yeah, as I mentioned, the flux of the secondary is around 15% that of the primary, and we can see the specific, we're able to retrieve the specific separation of the two stars as well. So this is the X position of the secondary and its Y position as well. And in this study that we did, where we were doing a survey of around 30 B stars, we were basically trying to detect any companions in the interferometric range, and we wanted to determine how significant those companions were. So the modeling or the tool that I used to model these systems is called PMARED. This is parametric modeling software developed by Antoine Moron, who's from ESO in Garching. He's a VLTI system scientist. And yes, he's really put together this beautiful parametric modeling code, which allows you to incorporate many different kinds of geometrical components to simulate what you're observing with the VLTI, whether that's disks, for example, planet-forming disks, protoplanetary disks, or different kinds of stars, resolved stars with a structure, for example. There's a huge amount of a possibility that you can do with this. And one of the coolest tools within that code is the fact that you can check for the significance of your companions, and also you can do grid searches. So basically what I've done here on the left is that I've performed a grid search over this range of separations, so going from plus or minus kind of 50 milliarc seconds in X and Y. And this has enabled me to find the most likely position for this companion using chi-squared analysis. So here you can see this is the best fitting solution. But then on the right here, it's also testing the significance of the companion. Now this becomes numerically degenerate at a certain point, but basically up to about 8 sigma detection significance, we are pretty safe. And so basically what this is showing here is not only, so this is where the chi-square search allows me to find the most likely position for the companion, and the doing the significant test on the right allows me to determine, okay, is this actually significant in terms of its flux? So this is what we are looking at on the right here. Okay, so once we found a number of, so basically what I did is I performed this kind of parametric modeling analysis for a sample of around 30 stars, 32 stars. And I then wanted to, after we had found the results, which I'll present in a second, we also wanted to make sure, okay, are we missing any, what is the likelihood that we're potentially missing companions within this data set that we're looking at? And so with Uxana, my collaborator, we did some statistical tests to determine our detection probabilities and basically and work out, what is the likelihood that we are missing or missing some potentially companions. So I used a multicolor approach to do this, and what we did is we would simulate a population of B stars. If you want to look at the method in more detail, you can check out this paper from 2013 or another paper of Bernsteiner 2021. And we applied detection criteria specific to the different observations that we were looking at to evaluate the likelihood that a companion would be detected. So we put in various, we assign certain distributions to the simulated population of B-type stars. We assumed an opaque law for orbital periods. We assumed a uniform mass distribution, power law distribution for eccentricities, for example, and random orientations of the orbital plane. Oh. And so essentially, this is what we saw here. So I'm going to describe a little bit more, but for now I'll just focus on this plot in the bottom, this bottom left. So here for our interferometric data, this basically shows the detection probability that we would have for detecting a companion from the simulated B-star population. And so, and we also combined our interferometric data with spectroscopic data from the literature, which is why we have the spectroscopy up here, and we have the combined method down here. And I'll talk about that a bit more in a second. Mostly what we determined is that we have a detection probability of 99% up to periods of 1,000 days, and mass ratio is down to 0.1. And so based on this high detection probability, we consider that the multiplicity fractions that we find, that I'll present right now, we do not need like a significant bias correction down to Q equals 0.1 and periods of a few years. Okay, so what did we find? I mentioned that we looked at a sample of around 30 B stars, and this is the interferometric multiplicity fractions that we found. So this is just looking at the Pioneer data that I was using. So we found that we had most of the systems were binaries, and second most common system was a single, and we also had a couple of interferometric triples as well. And you can see the kind of distribution in terms of flux ratio and separation here. And yeah, the triples are shown in yellow and the binaries are in purple to match this pie chart here. And also if you can squint, you can also see that, so if you see a cross, this is a tertiary companion rather than the secondary companion. But we also, as I touched on earlier, wanted to combine the findings that we found from interferometry with other information from the literature. So I did a literature search to look for previous detections of spectroscopic companions around the systems I was looking at as well. But also we, with further collaborators, we looked at checking Gaia as well. Gaia can obviously detect, is operating as quite a powerful binary detection engine at the moment, thanks to the fact that you can find companions thanks to the astrometric wobble that Gaia can detect. So we also just searched the Gaia DR3 database for our sample to see if there was any wider companions that we could detect from there as well. And so you can see the spectroscopic results above, and we can detect a couple of companions with Gaia as well. And when we combine all of that together, so taking into account the companions that I detected with interferometry, with those existing spectroscopic detections and also the Gaia detections, the pie chart changes significantly. We still have binaries as the most common system, and we still have some singles, but the number of triples increased a lot. And the way that this usually worked is that we were finding a third companion with interferometry around an already detected spectroscopic binary. We did tests to determine if the likelihood that a spectroscopic companion that was detected would be the same as the one we detected with interferometry. So that's been taken into account here. We were only really expected to detect very long period spectroscopic binaries as interferometric companions, and so this is what we took into account. So basically what we think is that we're actually detecting a number of hierarchical triples, essentially, when we combine spectroscopy, interferometry, and Gaia. And I think that's interesting because there's a number of, because higher order multiplicity, I already mentioned how binarity can already have huge effects on the evolution of your stars, as they transfer mass, as they interact and potentially cause mergers. But higher order multiplicity can also push systems into interesting effects as well. Particular common effect that is discussed is the Kozai-Leidov effect, where if you have a tertiary star, perturbations from that tertiary can affect the orbit of the inner binary. This depends on the inclinations between that kind of outer orbit and the inner orbit that you have. But they can excite eccentricity of the inner binary and prior to the onset of mass transfer. And a nice study by Flores Kummer and collaborators which came out in 2023 was looking at kind of the change in kind of the behavior of a binary when you put a tertiary companion outside, and they found the following. In particular, what I think is very interesting is that not only does the presence of a tertiary increase the likelihood of mass transfer in the inner binary, it also causes it to start earlier, which I think is very significant if we're thinking about the fact that we need multiple interactions to get to particularly these compact object measures that I was talking about earlier. There's a couple of things that we want to continue from the study of the B-star multiplicity with interferometry, and we have a couple of surveys ongoing, particularly to monitor these things over a much longer time frame. And the reason we want to do that is precisely so we can define these eccentricities, define the inclinations of the orbits, which are very important into investigating the effects of this higher order multiplicity on the evolution of these systems. So stay tuned for that. Okay, the last thing I want to do is talk about one other way that spectrophotometry can give us some fun information on B-star multiple systems. And this is by looking at specifically spectrophotometry versus the interferometry that I mentioned before. So here on the right, you can see the inside, or a schematic of the inside of the other instrument at the VLTI. I already mentioned Pioneer and Matisse, but now I want to talk a bit about gravity. And this is a spectrophotometer that exists at the VLTI. And essentially, in order to turn an interferometer into a spectrophotometer, you have to, in the most simplistic terms, add a spectrometer into your beam combining instrument. And this allows you to now get a new set of observables that you can use to probe your system, as well as the visibility and the closure phase that I mentioned before. Particularly one of these very powerful observables that we can get is the differential phase. And so essentially what happens is that if you have an emission line coming from your source, which as from stars we usually do, we often do, you can use that emission line as a reference point to look at the kind of displacement between that emission and the continuum coming from your source. And this allows you to essentially just get a new handle on your system. And so in a way that the closure phase is using kind of the spatial offsets from the spatial positions of the telescopes as a way to retrieve some phase information from the source. Now we're using kind of the changing wavelength to get some additional phase information on our source. And you can already get some spectrum from your spectrum interferometer. Usually our resolutions are much less than a dedicated spectrometer, but still it can provide us with a lot of extra information. And so again, thinking in simple terms, the shape of our differential phase can already tell us something about the processes that are happening. For example, an S shape can tell us about a rotating structure, and a W shape can tell you about an expanding structure, for instance, maybe like a shell around an evolved star. And so here on the right, to show the kind of the extra information you get, this is actually a study of a protoplanetary disk. But what we're seeing here is that the continuum emission coming from this source, so that's just, from your again, this is gravity data, so coming from like your K-band continuum, if you like, is shown in gray here in the center. But basically what the bracket gamma is showing us, so that's the emission line that we are using in this case, is actually tracing a very different scale within this disk, and also tracing a different kind of process that's happening in the disk. And basically what they concluded here was that, so the bracket gamma line here is tracing kind of a disk wind on the very top level of the disk, while the continuum emission that was detected with gravity was really localized to the very inner disk rim. So really you can get a much broader view of your system if we're using these differential phases. And so to bring us kind of back to B-stars, I just wanted to present again another work that I did where we were using the spectrophotometric capabilities to really kind of decide between two cases for a B-star system. So before I go into kind of this case itself, I just want to very quickly talk about BE stars, because this was integral to this kind of story. So BE stars are, the E dictates, as many of us know, the emission. So, generally, BE stars are just non-supergiant B-type stars that show hydrogen lines in emission. And so within that kind of group, the most common kind of BE star is the classical BE star, which is a very rapidly rotating B-type star surrounded by a gaseous kind of accretion disk of self-ejecting matter. There's not much dust here. There's no dust here. They're often Keplerian rotating. And because of this presence of this accretion disk, and depending on how the angle that we are looking at our B star, we can see short-term periodic variability towards these rapidly rotating B stars. And you can see how a spectroscopic line profile will change depending on that angle we are looking at the disk here. And we expect a large proportion of BE stars to exist in binaries, and a number have been found in a post-mass transfer state. Here's a little cartoon, just showing potentially one way that a binary interaction could help us to create a BE star system. Again, mass transfer will begin. You'll have Rho-slope overflow coming from the slightly more massive star in the system, and this transfer of mass can then potentially spin up your companion star, turning it into a BE star, and potentially you will be left with, once that mass transfer has happened, you may expect to see the BE star surrounded by, or the companion to the BE star as a strip star. And eventually this can eventually go into a supernova, and maybe be left with a BE X-ray binary, sorry. Sorry. But, the origin on all BE stars and the origin of the rapid rotation is still not, completely constrained. This is one potential channel we can use to get this fast rotation that we see for these stars. But also, this could also be explained by stellar evolution of the main sequence, particularly as the core contracts and speeds up rotationally, and the photosphere expands, and this can also cause this kind of rapid rotation that we see, basically this mismatch in the between core and envelope. Causes the angular momentum transfer between two regions, which can spin up the star. So there's still, there's multiple ways that this spin up could happen, and these are just a couple of the ways that this is been proposed. So the reason I introduced BE stars is because the system that I want to talk about, where kind of spectrum interferometry really kind of saved the day, was a system where we knew there was a BE star, and we knew there was some kind of B star as well. But the true nature of the system was a bit difficult to work out. And so the system that I'm talking about is called HR6819. And in 2020, this system caused a lot of fuss because it was claimed to be a triple system containing the nearest black hole to Earth. And this was a study from a study of multi-epoch optical spectra done by Rubidius in 2020. And basically, they were looking at the movement of the emission lines in their spectra, and they were basically decided that, okay, we think we see if we think in order to explain the movement of the lines that we're seeing, that we need to have an unseen companion, and that, given the masses that we calculate, needs to be a 4 solar mass black hole. And so this is kind of the schematic they proposed. They proposed that there was a black hole in a close orbit with a B star, and then they would have a B star on a much longer orbit around them as a tertiary. And so this was fun, but it was disputed. So there was an alternative explanation was proposed, basically by using spectral disentangling methods on the same spectra that Rubidius had used. They decided to target alternative spectral lines, and basically were able to distinguish that you were seeing variation from both stars. So you didn't need an unseen companion to explain what was seen in the optical spectra. And they instead said that, okay, it's not a system with a black hole, but it's instead a close B and stripped B and BE star binary. And so we had these two stories from spectroscopy, basically where the VLTI came in and where gravity came in was that we kind of wanted other observations to determine or decide between these two scenarios and determine the true nature of the source. And so that's where I kind of joined this project and where gravity came in. And so here we can see the observables that I mentioned earlier. So now we have the normalized flux on the left. We have the closure phases that I mentioned earlier. We have the differential phases here, and we have the visibilities again. And again, here you can see the model that I'm getting from fitting these observables. So in this plot, the red is the model, and the black is the data, and the gray are the errors. And so the first model that I did was just a simple kind of binary model, and that you can see being fit here. And you can see that, yeah, it provides an all right fit generally, but key things are missing. And the first thing is this beautiful double peak feature that we are seeing in the normalized flux. And also the shape of the emission line feeding through into the differential phases is off. There's definitely some improvement to be made here. Because we see a double peak structure, that's kind of indicative of a rotating structure. And so we're like, okay, maybe we are resolving, or not resolving, but through spectral interferometry, we are getting some probe of this secretion disk around a B star, the E star. And so we decided to try and replicate that. And so what we did is, this was actually kind of tricky. This is because I mentioned that the VLTI has a spatial resolving powers of kind of like up to a few milliarc seconds. But here we're dealing with a really, really small disk. Diffusion disks are very, very you know, and not as extended as kind of 3 milliarcseconds, particularly in this system. And so what I had to do is I had to kind of break down this double peaked emission into not immediately going for a disk model because it's kind of we're below our resolving power, but I wanted to try and break it down into different components. So I created a blue shifter component, a redshift component to kind of represent this double peak that we're seeing in normalized spectra. And that's what you can see here, just kind of a simple toy model. And then once I had these components well constrained in the fitting process, I could expand it into a disk fit. So you can already see through this toy model, but breaking it down into kind of blue and red shifted emission, that we already see an improvement in the fit to this bracket gamma profile, and the fit to the differential phase is also improved. And then using that as a starting point, I was able to converge on a robust disk fit as well. So here you can see the this kind of final disk fit. This is just showing it in two different velocity channels, which is why you see the flip in this here. But as you can see, this much better reproduced the double peak that you can see here, and also much better reproduced the signal that we were detecting in the differential phases. And yeah, in this plot here, sorry, this is the UV coverage that we had as well. And so this seemed to show that we had two sources of very, very close separation of order kind of 1 millisecond. And again, this is below the spatial resolving power of the VLTI, but thanks to the fact that we have our spectrometer and we have this probe of an emission line, we're able to get information on much smaller scales than the actual physical limit of the interferometer. And that's really, I think, the key like special power of having the spectrometer in your interferometer is that you're able to do this. And so we knew that we had a system with two bright sources, so a very close separation, and we likely have this Keplerian rotating disk structure. And we also, you know, looked at some additional data from Muse to double check that we didn't have a companion at large separation like the black hole theory required. And indeed, we did not have this large source at a bright source at 100 milliarcsecond separation, and we did have two sources close together. And so essentially, that's why we were able to conclude, okay, we don't think we need a black hole to explain the system. It can just be explained as a post-interaction BE star system where we have a stripped B star companion, around this BE star with its duration disk, which we could probe with interferometry. And so I think I've talked a lot, so I will just wrap up. I hope I've convinced you that interferometry can be a really nice tool to probe the multiplicity of B stars and its effects, and particularly that spectrum interferometry can really help if you have like a system which is difficult to determine the origin of with spectroscopy alone, for example. It can really help you to determine exactly where your emission is coming from and to help characterize the stars in your systems. So both of the papers are out that I've talked about today, so please feel free to check them out for any more information. And yeah, thank you for having me, and I will take any questions. Thanks very much.
Great. Thank you so much, Dr. Frost. I see a lot of applause in the reactions. So we've got a good amount of time for questions. So we'll open up the floor to any questions people may have. If you're having trouble with your audio, you can also drop questions in the chat and I'll read them out loud. So maybe I'll kick off with one. Apart from binaries and these are this spectrointerferometry technique seems really interesting. And are there other science cases in the general massive star kind of field that you could expect to use it for?
Yes, so there's a few colleagues I have who are looking at supergiant stars, because you're actually able to, well, for some of the closest ones, you're able to resolve kind of the surfaces of these systems. This is usually used a lot more with kind of I have a colleague, Julian Dravon, who's also who's a fellow here. He works at resolving the surface structure of these stars. So it's basically through a technique called image reconstruction. So in the data that I showed, it's kind of a snapshot mostly. So you take one observation, but if you do lots of those snapshots over time, you can start to try and you get enough sampling of your UV space that you can try and reverse engineer an image from that. And so he likes to do kind of surface studies of these objects using mostly Matisse, so the slightly longer wavelength instrument, but this is also possible with Gravity and Pioneer as well. And this should be possible for other kinds of any star which is extended enough for you to resolve. You can start to try and do this. It's obviously easier the closer it is, because then you have a big area to work with. But this is also something that people are doing, for example. And yeah, also on the formation side, I know I have a number of colleagues who are looking at massive forming stars, or MOSOs, pre-main sequence stars, trying to resolve their disk structure. There was a nice study by and also De Kink, who is looking at pre-main sequence OMB stars, trying to look at the kind of and also Frank Bax as well. And they've been looking at using spectrointerferometry to probe the inner disks of those forming stars to try and better understand the kind of the accretion processes that are potentially happening to build up these OMB stars before they reach the main sequence as well. So yeah, there's plenty to do with this technique, for sure.
Very cool. So we do have one question in the chat from Doug Guys. What kinds of companions do you find in the B star triples?
Yes, so the tertiaries were almost always low mass in companions. There are a couple of cases where we have a quite more massive tertiary companion, for example. But yeah, generally they are kind of the order of like Q equals 1.5, Q equals 0.15 or 0.2 in terms of these in terms of the mass ratios for these stars, which are inferred from our flux ratios, because in order to get dynamical masses, we need to take more epochs of data, and that's what we are also doing as part of this ongoing survey to monitor these systems. So yeah, we're inferring the mass of the system from the flux in this case. But yeah, stay tuned for the eventual dynamical masses of these things as well. Yeah, and I see a second question as well. Will Gravity Plus extend the dynamical range of binaries? This is a good question. We're certainly going to be able to push to fainter. Well, actually, I think the main benefit of Gravity Plus is that in interferometry, I mean, especially with the VLTI, we're limited in terms of like where we can observe. You need to have a bright fringe tracking star or a bright guide star in order to observe your source. Because yeah, you lose a lot of your flux when you're doing interferometry, so you need to have bright reference stars in order to do this. And so I think the key thing that's exciting to me in terms of Gravity Plus is that I think we're going to start finally being able to look at the Magellanic Clouds for the first time and start to probe, stars there with interferometry, which I think is very exciting. And the first kind of the science verification data for that is going to be coming in January, between January and April next year. And I know there is a number of programs which are looking at quantifying multiplicity of stars in the Magellanic Clouds for the first time, both forming stars and on the main sequence as well. And yeah, generally now with Gravity Plus, we are be able to go much fainter. So I think the magnitude distance difference that we will reach is now 22 mag in contrast, which is opening up a whole new parameter space of kind of smaller companions for us to find and look for. And so yeah, I'm really excited to see what comes out from these first Gravity Plus observations and see how much more we'll see what we've been missing essentially with the current instrumentation. So it's exciting times.
Great. Are there other questions for Frost? Okay, so in that case, I just want to thank Dr. Abigail Frost once again for a wonderful talk and really nice work. Looking forward to seeing the next steps. I'll also remind everyone that these talks are recorded and are on our YouTube channel. So if you have colleagues who really wanted to make it but unfortunately couldn't, then you can point them to our YouTube channel. You can also find all of our previous talks from the last couple of years there. Thanks again for attending today's seminar. We'll be announcing the next one, which will be occurring in 2 months. And I will be correcting the title of the email that I send everyone to say bi-monthly. And once again, thank you, Dr. Frost, for kicking off the 25-26 season. And see you all in two months.
Thanks again. Thanks for having me. Bye.
Bye-bye.